Hello students, after de Broglie and Heisenberg's uncertainty principle, the next topic for class 11th in second chapter is spectrum. Now what is meaning of spectrum? How can we obtain spectrum? And what are the outcome of spectrum? This we will discuss in this chapter. So first, what is meaning of spectrum? You all have seen rainbow, and you all know that rainbow has seven color, and all the seven colors are always arranged in the same sequence. It is Vibgyor, you all know. So they are not seven colors for us now. In fact, these are seven different radiations, and they arrange in increasing order of wavelength. The violet color has wavelength near about 400 nanometer, and red color has wavelength near about 750 nanometer. And this particular arrangement of radiations in increasing order of wavelength, or you can say decreasing order of energy, is known as spectrum. So just look at here, how can we define it? Arrangement of various radiations in increasing order of wavelength or decreasing order of energy. So this is one of the best example of spectrum which you have seen in day-to-day life. But rainbow is not only the example of spectrum. This is only just a single example of spectrum. Now spectrum means, so far it is arrangement of radiations according to its wavelength. There are two type of spectrum. One is known as continuous spectrum and other is known as line spectrum. The difference between continuous spectrum and line spectrum is, you can see here, when you saw the rainbow, these colors are not well separated from each other. In fact, each and every color is blend to the next and previous color, and therefore there is no gap here, and it is known as continuous spectrum. But when we obtain the spectrum of an atom, the radiations are quite far from each other. In fact, two radiations are quite separated from each other. For example, if same type of spectrum is obtained for an atom, then here you can see we get three color here. It is blue color, green color and orange color, but the remaining color are not finding here. The radiations, these are three radiation. This is first, this is second and this is third. These three radiations are quite separated from each other, and such type of spectrum is known as line spectrum, where radiations are separated from each other. Here radiations are blend with each other, next and previous, and that is known as continuous, and this is known as line spectrum. Whenever you will obtain spectrum of an atom, it will be a line spectrum. This is also known as discrete spectrum because the radiations are quite far away from each other. Now, how can we obtain the spectrum of an atom, and why an atom produce such type of spectrum? To discuss it, look at here. You know that an atom can have infinite number of shells, and each and every shell has definite amount of energy, which you can calculate with the help of Bohr formula. Bohr formula for energy, it is minus 13.6 into z square upon n square. This formula is given by Bohr to calculate energy of electron in the atom, where z is number of shell and z is atomic number and n is number of shell. Now we will discuss later on that there is a drawback in Bohr atomic model, that it is applicable only for single electron system. So this we will discuss later on. But suppose we are doing the calculation for hydrogen atom, then atomic number Z is equals to 1, and the number of shell, it may be 1, 2, 3, 4, 5, 6. Remember, an atom can have infinite number of shells, because shell is not a constructed area where electron revolve. In fact, shell is the path where electron revolve. If you increase energy of electron, then electron revolve at a longer distance from nucleus, and it will be its next possible shell. So Z equal to 1 for hydrogen. Suppose we are calculating for first shell, then its energy will be 13.6. In fact, minus 13.6. The unit of this is electron volt per atom. So this is energy of electron in the first shell. Similarly, you can calculate energy of electron in second shell. You have to change the value of n. Earlier we take 1 because of first shell, now it is 2. 2 square will be 4. 13.6 divided by 4, the answer will be minus 3.4 electron volt per atom. So in this way you can calculate energy of electron in first shell, energy of electron in second shell, energy of electron in third shell, up to infinite shell you can calculate. For third shell we will divide 13.6 by 9, and therefore the answer will be near about 1.5 electron volt. For fourth shell you will divide by 16, answer will be near about minus 0.8 electron volt per atom. So you can conclude here the energy of first shell is minimum because they are in negative number. So you can see here energy of first shell is minimum, second is more, third is further increase, fourth is further increase. It means as the number of shell increase, energy continuously increase. But here at the same time you can also see, although number of shell increase and energy increase, but the difference of energy between two successive shells continuously decrease. Two successive shells continuously decrease means you can see here 13.6 and 3.4. The difference of energy between first and second shell is 10.2. The difference between first and second is 10.2. Difference between second and third, it is now only 1.9. And difference between third and fourth, it is only 0.7. So the maximum difference between first, second, then it is second, third, and in between third and fourth, the difference of energy is minimum. So conclusion, when we increase number of shell, energy will increase, but the difference of energy between two successive shells continuously decrease. Now in hydrogen atom, in fact in all the atoms, especially in hydrogen atom, because Bohr atomic model explain the features of hydrogen atom only, we know that electron revolve in first shell, and now because energy of each shell is constant, therefore the shells can also pronounce as energy level. I repeat, because the energy of each and every shell is constant, so shells can also consider as energy level. And therefore it's not compulsory that always we draw shells in circular way. For understanding, I am drawing the shells like this. This is nucleus, this is first shell, this is second shell, this is third shell, this is fourth shell, this is fifth shell. These are different type of shells, different number of shells, 1, 2, 3, 4, 5. We know that electron of hydrogen atom in normal condition found in first shell. Now wherever electron found in normal condition, this is also known as ground state. Ground state means it is the common state, it is the general position of electron. So electron found in first shell in hydrogen, and it is known as ground state. Can you shift the electron from ground state to first shell or second shell, ground state to second shell, third shell, fourth shell, fifth shell? Then answer should be yes. We can shift electron from ground state to second, third, fourth, 5. In fact, up to infinite shell you can shift. And this is as simple as, if I ask you throw a ball in air, can you throw a ball in air? Answer is yes, you can throw the ball in air, and the distance traveled by ball in the air depend on how much energy provided from our side. If we give more energy, then ball will travel long distance in air, and if we give less energy, then ball will travel less distance in air. Same goes here. Electron will shift from ground state to higher energy level. Now these higher energy levels are also known as excited states. The second shell in hydrogen atom, this is second shell, and it will be considered as first excited state. I repeat, the second shell will be considered as first excited state. Similarly, the third shell will be considered as second excited state. The third shell will be considered as, just give answer. I repeat, the second shell is considered as first excited state, third shell is considered as second excited state, fourth shell is considered as third excited state, and you know the first shell, very first shell, is also known as ground state. So we can shift electron of hydrogen from ground state to excited state. Now the distance traveled by electron definitely depend how much energy provided by us, and therefore electron can jump from first to 5, electron can jump from first to 4, first to 3, or first to 2, depending how much energy is given by us. Now once again recall the ball which you have thrown in air some times ago. Will the ball stay in air? Answer is no. When you throw ball in air, ball once again come to the ground. The reason is, here the energy of ball is maximum, and there is a simple relation between energy and stability, and this help you in a number of topic in class 11th and 12th in chemistry. That is, energy is inversely proportional to stability. A stable substance must have less energy, but because here energy is maximum, so stability is minimum. To regain stability, the ball again move toward ground, and just like here, you forcefully shift electron or throw electron in higher energy level, but electron will be unstable here. Electron definitely return in ground state. When electron return in ground state, it lose energy, and this lose energy, this released energy, we observe, and this is known as spectrum of atom. In fact, because these radiations are released, therefore this spectrum is also known as emission spectrum of atom. Now here a few questions. Will electron, when electron return, will it lose a single type of radiation? Will electron lose a single type of radiation? Then answer should be no. To understand this, look at here this example. Suppose I kept some balls here, and these are staircase. You kick these balls, and the ball will travel to ground. Now, is it compulsory that ball travel only this particular, ball use only this particular path? Then once again answer is no. Balls can be used this path, balls can be used this path, or balls can be used this path also. So the various path can be taken by ball to come on ground. Same goes here for electron also. When electron return in ground state, it's not compulsory, it's not necessary that electron will return directly from fifth shell to first shell only. Yes, electron can return from fifth to first shell directly also, but at the same time electron may shift first from 5 to 4, then 4 to 3, then 3 to 2, and then 2 to 1. Such type of transition, in fact other possibilities like 5 to directly second shell and then second to 1. So all this type of transitions are possible, and therefore we will not have a single type of radiation when electron return from higher energy level to ground level. One more point here which should be remember, hydrogen has only single electron. So only one electron, if there is only one ball, so it should have only one type of path. But once again here a problem, you cannot take the spectrum of a single hydrogen atom. You know, single hydrogen atom cannot be seen, cannot be taken for experiment. So when you take billions of molecule of hydrogen atom, so they have one electron in each. In some of the atom, the electron can shift directly from 5 to 4, directly from 5 to 1. In some other atoms, the electron may use these type of transitions. So we will not have a single radiation in spectrum. In fact, we have a number of radiations in spectrum of hydrogen atom. At the same time, remember one more point. Will we have all possible type of radiations in spectrum? Then answer is no. If we will have all the type of radiations, then if you remember this particular, then these should not be black. Here also we should have radiations. So we will not have all type of radiations. And the reason for this is there is a difference between Bohr and electron. You know that energy of first, second, third, fourth, fifth shell, these energies are constant, and therefore electron can emit only certain specific type of radiations also. For example, if you remember, the difference in the energy of first and second shell is 10.2. The difference between second and third we have calculated earlier, it was 1.9. So when electron return from third to second shell, it will emit 1.9 energy only. If electron return from second to first shell, it will release only 10.2. So we will get definitely 10.2, we will get 1.9, as well as we will get 10.2 plus 1.9. It becomes 12.1. This also we can get if electron directly return from third shell to first shell. But 10.21, 10.22, 10.23, this type of radiations will not observe here, because the energy of each and every shell is constant, and this will not possible to change the energy of these particular shells. So difference is constant, and because this difference is constant, it will emit a particular type of radiations only. Now look at here, this particular diagram. This is also known as emission spectrum for hydrogen atom. This is first shell. Now you know it is also known as ground state. This is first excited state. This is second excited state. This is third excited state. And the number of shells are 1, 2, 3, 4, 5, 6, as you have used in lower classes also. Suppose we exposed atom with radiations, and now electron is excited. Electron may be present in second shell, third shell, fourth shell, fifth shell and sixth shell. And how it is possible that electron present in all possible shells? Because we cannot conduct spectrum of single atom. There are billions of atoms. So in few of the hydrogen atom, the electron may be present in second shell. In other, it may be in third shell. In other, it may be in 4, 5, 6, 7, 8 shells. So here we take 6 shell to understand how we will get spectrum. So electron already excited. We know electron will return in ground state to gain more stability. When it return in ground state, it will release energy, and this energy in form of radiations construct spectrum, which is known as emission spectrum of hydrogen atom. Now suppose electron, first possibility, electron directly return in first shell. Whether it is in second shell, it directly return in first shell, or from third shell, or from fourth shell, fifth shell, sixth shell. So first possibility, suppose electron directly coming in the first shell, it returned in the first shell, maybe from 6, 5, 4, or it may be from third shell, or it may be from second shell. So electron return in the ground state. This is first possible transition. Now here the energy of emitted radiation is very high, because you know the difference of energy between first and second is highest. Out of two successive shells, the difference between first and second is highest. So when the difference between first and second is very high, the difference between third and one, fourth and one further increase. They all have high radiations, high energy, and they all belongs to ultraviolet radiations. These radiations observed by scientist Lyman, and that's why they are also known as Lyman series. Now second possibility, here electron return in first shell. Second possibility, suppose electron return in second shell instead of first shell. Now electron return in second shell. So when electron return in second shell, you can see here from 6 to 2, 5 to 2, 4 to 2, or it may be 3 to 2. So electron now return in second shell. This time the energy of radiation will be little bit low, and therefore these all radiations belong to visible region studied by scientist Balmer, and therefore that's why they are known as Balmer series. Now, will electron stay in second shell? Answer is no. Second shell say electron will jump from second shell to first shell, no doubt. But no need to draw that radiation. No need to draw this radiation. The reason is here our aim to find out how many type of radiations emitted by electron. Now this radiation and this radiation, they have same energy. So if you draw this, you may wrong in your counting. So do not draw here. We already counted how much energy released when electron return from second to 1. So this radiation we already taken up. So do not draw this radiation. And instead of this, excluding this, if you calculate the energy of now 1 2 3 4 5 6 7 8 9, this all 9 radiations have different type of energy. It means there are 9 different type of radiations. If you draw this, then it will be not 10th one because they have same energy. So electron return in second shell, Balmer series visible. Next possibility, electron return in third shell. Once again from any higher level, return in third shell, energy further decrease. They are in infrared region given by Paschen, and that's why it is known as Paschen series. Once again electron will not stay in third shell, it come down in the ground state. No need to draw this line because we already draw this radiation 3 to 1. So here you can see electron return from third to first, and we already taken up this radiation. Another possibility electron may return from third to second and then second to 1. So that also we have already accounted here. This is third to second and this is second to 1. So 3 more type of radiations we can have because of this possible transition. Another possibility, now electron first return in fourth shell given by bracket, and this also lie in infrared region. And once again 4 to third, third to second, second to 1 we already counted. And last possibility, electron return from 6th to 5th shell first, and series is given by P fund, and this is also in infrared region. So these are various possibilities when electron return from higher energy level to ground level. Now one very interesting point, the amount of radiation, be concentrate here, this is very important point here. The amount of energy released during this transition, in fact you can say the energy of radiation depend on the difference of energy between two shells, not successive, between two shells. The energy depends on the difference of energy between two shells, and therefore these radiations have a definite amount of energy. Now look at this formula once again. Here Z is atomic number. So if you change atom from hydrogen to other atom like helium or lithium, the value of Z will change. The difference of energy will change, and therefore here the wavelength of the radiation will change. So in fact you can say that each and every atom has definite pattern for emission spectrum, and therefore emission spectrum is also known as fingerprint of an atom. An atom can have a unique type of spectrum which cannot be copied by other atom, which cannot be similar or identical for other element. So there are few questions we will discuss later on. Though spectrum part has deleted from your syllabus, but still it's good idea to prepare at least this much part. We should remember this name of the series, Lyman Balmer Paschen bracket fund. Whenever electron return in first shell, it is Lyman series. Electron return in second shell, it is Balmer series. Third shell, it is Paschen series. Fourth shell. You can ask a question here, how many total spectrum lines, the radiations are also known as spectrum lines here, how many total spectrum lines are obtained here? So right now you can count here 5 plus 4 plus 3 plus 2 plus 1, it is 15. But you have a formula also here, you can use a formula, it is n into n minus 1 divided by 2. This is formula to calculate total number of spectrum lines. And here n is the maximum shell from where electron return. In this explanation, I take maximum number of shell as 6. So when I place the value of n6, it is 6 into 5 divided by 2, and therefore it is 15. So total 15 spectrum lines are obtained here. When electron return from maximum of 6th shell, if you start with 7th shell, then place the value 7 here. It will be 7 into 6 divided by 2, and therefore it will be total 21 radiations, 21 different type of radiations will be observed when electron return from higher energy level to ground state. Now next topic is Bohr atomic model. There are four important points with respect to Bohr atomic model. The first is electron revolves around nucleus in a circular path having definite energy. This we have discussed now. Definite energy. This path is known as shell, orbit, or energy level. So you have used this term earlier, shell or orbit, but a new term is energy level because the energy is constant. So you all know electron revolve, and now a new point is the energy of shell is constant, definite energy. Second point, for an electron, only those orbits are possible in which angular momentum of electron is multiple integral of h upon 2 pi. We can convert this statement into this formula. As per this point, the angular momentum of electron, which is given by mvr, must be equals to nh upon 2 pi. Here n may be 1, 2, 3, 4, any integral number. And if this equation is satisfied, then only this particular radius is possible. It means only in this condition electron can revolve in that particular shell. I repeat, what is meaning of this statement? You can compare this first and second. First says electron revolve around nucleus in a circular path having definite energy. So suppose this is first shell and this is second shell. Why can't electron revolve here? This is first shell and this is second shell. Energy is minus 13.6, we calculated earlier. Energy of this is minus 3.4. So why not electron? Why can't electron revolve in between these two shell? The reason is given by Bohr. According to Bohr, only those particular shells with radius r is possible if this condition is fulfilled. Explanation is not in our syllabus, but we can discuss later on why this is so. mvr equals to nh upon 2 pi. Third point, while revolving electron in a particular shell, when electron revolve in a particular shell, electron neither lose nor gain energy. So when electron revolve here, it is first shell minus 13.6 electron volt. It is its energy, and this energy always remain same, constant. It will not lose energy, it will not gain energy. Fourth point, if electron absorb energy. Now here this you might have some confusion here. Here we told that here we discussed that energy neither lose nor gain, and here we start if electron absorb energy. So in which condition electron can absorb energy? If we expose atom with certain amount of energy, if forcefully we give energy to the atom, in fact energy to the electron, then electron has to absorb this energy. So if electron absorb energy, it will shift in higher energy level. This we have discussed in the spectrum. Electron shift in higher energy level. In high energy state, it will be unstable and return in ground state by loss of energy. We know here it is unstable, it return in ground state by loss of energy. The absorbed and emitted energy, when electron move upward direction, it absorb energy. When electron return in ground state, it release energy. The absorbed and emitted energy is quantized and given by delta E equal to final energy minus initial energy. Now quantized means they have definite amount of energy, or we can say same amount of energy. If it absorb x joule here, it will release same x joule here. This is meaning of quantized energy, and this is a confirmation that energy of each and every shell is constant. Otherwise the value of these two should be different. When electron jump and return, if the energy of shell change, then the value of this should also change. but always this energy remains same, and this is a confirmation that energy of each and every shell is constant. So you can calculate by delta E equal to E final minus E initial. This is energy of final shell and this is energy of electron in initial shell. Applications of Bohr atomic model. Here we have some applications. Bohr gave some formula to calculate energy, radius and velocity of electron in an atom. The first is to calculate energy. E equal to minus 2 pi square k square E4m z square upon n square h square. Now do not scared. You are not supposed to prepare this formula for class 11th. For competitive examination you should memorize this formula. Here 2 is constant, pi is constant, you know, k coulombs constant, this is also constant. E is charge of electron, m is mass of electron, z is atomic number, n is number of shell, h is Planck's constant. So if you carefully look this formula, only there are two variables. One is z, that is atomic number, and other is number of shell. Rest all are constant. 2, pi, Coulomb's constant, charge of electron, mass of electron, and Planck constant. So when you put the values of this constant and you solve, you will get this final formula which you have to remember for class 11th. It is minus 2.18 10 s power minus 18 into z square. You can see here z square and divided by n square. Z is atomic number, n is number of shell. The unit is joule per atom. Or we can change the unit from joule to electron volt. We know the relation between joule and electron volt. 1 electron volt equal to 1.6 10 s power minus 19 joule. You can use the same equation and remember this formula also, which we have used in spectrum, minus 13.6. The constant will change, rest is same, z square upon n square. One more possible unit, kilojoule per mole, and it is minus 1312 z square upon n square. Out of this three, this is the better formula to be remembered for examination, because sometimes you need to convert energy into frequency or radiation. You need to use formula E equal to hc upon lambda, and you know that earlier when we did this question, the unit of energy was joule. So if you want to calculate frequency, wavelength or wave number, the energy must be in joule, and therefore this is better option over these two other possible options. So this is more important for us, and I have just transferred the same formula, a numerical for you. Now this is the solution. You can see here, as per the question, the electron is excited in electron returned from third excited state. As per question, electron returned from third excited state, and third excited state means it should be fourth shell. Remember, it is first shell which is considered as ground state, rest all are considered as excited state. This is first excited state, this is second excited state, and this is third excited state. So as per the question, electron returned from third excited state means from fourth shell to ground shell. So final shell will be first and initial shell will be 4. You can replace formula delta E equal to E final minus E initial. Final shell is 1 and initial shell is 4. Use the same formula, place the value of Z, which is 2 here because it is helium, and this is first shell. Once again Z is 2 for helium, and this is for second shell. 2.18 10 s power minus 18, you can take common. In fact, you can also take common 2 square, both side 2 square, and minus minus become plus, so you can shift this in front side and this you can shift here, and finally you can get this as answer. The unit, you know, joule per atom. And the other part of the question, you need to calculate its wavelength. For wavelength you can write E equal to hc upon lambda. Remember one point, here it was delta E and here we are using E. There is no difference, because do not go for symbol, just try to understand what is meaning of delta E. Delta E is amount of energy released, because here the amount of energy is going to release or absorb, therefore we are using a symbol delta. Otherwise, you can write this is in energy and this is also energy, so there is no difference here. Another point, do not carry forward this negative sign here for calculation. Two reasons. One, if you put this negative sign here in energy, then wavelength is negative, which is not possible, negative wavelength. And second thing, whenever delta E is negative, it does not means less than 0, but delta E negative means this is the amount of energy which released. In other word, you can say whenever delta E is negative, this is an example of exothermic process. I hope it is clear now. How can we get ionization energy? Ionization means electron should be removed completely wherever it is revolving. It may be possible that electron revolve in first shell. To calculate ionization energy, we shift electron from first shell to infinite shell. So here n final will be infinite and n initial will be 1. And in this way we can once again use same formula, delta E equal to final energy minus initial energy. Use the value and you can get ionization energy. Second application is to calculate radius. Once again, no need to remember this formula for 11th. You have to remember this one for 11th. It is 0.529 n square upon z. Unit is angstrom. So you can have simple numerical. You will be provided value of n, value of z, and you can calculate radius of atom. And similarly, third application for velocity. This is final outcome of velocity. It is in meter per second, 2.18 10 to the power 6 z upon n. This is in meter per second. One more numerical for you. Calculate ratio of radius for third shell of helium plus and second shell of lithium plus 2. Remember formula of R, it was 0.529 into n square upon z. This is the formula to calculate radius. Unit is angstrom. You have 3 minutes to do this question. Your time starts now. Now see the solution. Check the solution. Any doubt you can share. Drawbacks of Bohr atomic model. There are few drawbacks here. It is applicable only for single electron system, as we discussed so far. It is applicable only for hydrogen He plus Li2 plus, so applicable only for single electron system. It explains spectrum of single electron system. Bohr treated electron only as particle, ignored its wave nature. You know, as per dual nature, electron is both particle as well as wave, but Bohr treated electron only as particle, ignored its wave nature. This is another drawback. It is violation of Hinsberg uncertainty principle. You know, as per Hinsberg principle, it is not possible to calculate both position and momentum, or you can say it is velocity, simultaneously with certainty. But Bohr gave formula to calculate both position, it means radius, as well as velocity. So we can calculate now velocity as well as radius both for electron, and this is violation of Hinsberg principle. He was not able to explain origin of this formula mvr equals to nh upon 2 pi, from where he got this formula, so he was not able to explain. Otherwise, this formula is related to wavelength and circumference of a circle. You know, the formula of circumference is 2 pi r and the wavelength is lambda into n. N is number of waves. When you replace this with de Broglie formula, de Broglie principle, it becomes 2 pi r equal to h upon mv into n. And now you can see mvr equals to nh upon 2 pi. So from here you can derive this formula, but Bohr was not able to explain how this formula comes in his mind. Now he can't explain Zeeman effect and Stark effect. Now Zeeman effect means it is splitting of spectrum lines in presence of magnetic field, and stark effect means it is splitting of spectrum lines in presence of electric field. Now what is meaning of splitting of spectrum lines? Just look at here. One moment. Yes, just look at here. Here right now you can see 1, 2 and 3 lines. But when Zeeman applied magnetic field, Stark applied electric field, this line gets splits in 2 or more lines. For example, here right now you can see only one line, but in presence of magnetic and electric field, this line gets split in 2 or maybe 3 or maybe 4. Not only this, but all the radiation split just like this. And now Bohr was not able to explain how this line gets split in 2, 3, 4. This was the drawback of Bohr atomic model, later on explained in quantum mechanical model. So these all are drawbacks of Bohr atomic model, and in next class we start with quantum mechanical model. Till that, stay at home, read this, subscribe my channel. Have a good day.